This session, we shall learn how to use the chain rule together with the rules we have learned so far to find the derivative of composite functions. I believe you know what composite functions are. So let's take it that you have two functions, let's say f at s and then g at x. And then we are to substitute one of the functions into the other. So let's take it that we are going to substitute g at s into the function f at s. When this happens, we are going to get this f of g at x, and this is what we refer to as what composite functions. In other words, we call it function of functions or function within function. So you can see that the function g at x can be found in the function of f. So this is what the composite function I am talking about. So we are going to learn how to find the derivative of functions of this nature. So let's take it that the function g is differentiable at x, and also the function f is also differentiable at g at x. Then we are going to have a composite function which is what h at x is also differentiable at what x. Then we can say that the derivative of this composite function here is given as this. Now what this means is that we are going to differentiate the outside function which is f, and then we multiply it by the derivative of the inside function which is what g, which is g. Now to understand the chain rule very well, we first have to identify our inside function and then outside function. Now looking at this composite function, our inside function, we can see that our inside function is what g at x. That is what our written here. This is the inside function, and then the whole of this becomes our what outside function. Now what we do next is we then differentiate the outside function which is what f at g at x, leaving the inside function alone, and then multiplying it by the derivative of the inside function which is what j prime at x, and then we are good to go. That is what the chain rule is saying. Also, we can use the Leibniz notation to find the derivative of what composite function. So if we have, or if y is a function of u and u is a function of x, then we are going to have a composite function which is going to be in terms of f of g at x. Then the derivative of this function y, or this y, which is given as dy dx, is equal to, we are going to differentiate the function y with respect to u, and then we differentiate the function u with respect to x, and then we multiply them together, and then we are going to get what our derivatives. So we are going to take examples and then see how best we can apply these two methods. So we have the first example. We are to find the derivative of this very function. So all what we are going to do here is to identify our inside function and then our outside function. So you can see that our inside function is going to be this, and then our outside function is going to be the whole of that. So let's write it here. So we have our inside function. So let's call our inside function g at x is equal to 3x, and then we identify our outside function, and that is going to be f at x is equal to 3x plus 1 all raised to the power 4. So after that, we find the derivative of the outside function and then the derivative of the inside function. So the derivative of the inside function, which is given as g prime at x, when we differentiate 3x, we are going to get 3, and then when we differentiate a constant, we are getting 0. Then we move on to the derivative of the outside function, which is given as f prime at x. And then we just repeat what is inside the bracket, and then we subtract 1 from the exponent, and we are going to get what? 3. So this is the derivative of the inside function and then the derivative of the outside function. So we just take the functions and their derivative into the chain rule formula. So we know that our h prime at x is giving us, so f prime at g at x is this one. So we are just going to write 4 bracket 3x plus 1 all cube, and then we multiply it by the derivative of the inside function, this, and that is what? 3. So after that we just expand and then simplify. So we are going to get 3 times 4 will give us what? 12. And then we have 3 times 3x plus 1 raised to the power 3. We can leave it in this way form. So this is the derivative of the function here. Now with the same question, let's try to use the Leibniz method to solve the same question. So what we are going to do here is we are going to let the variable u be equal to the function inside. So we are going to let u is equal to the function inside 3x plus 1. If that is the case, then we are going to have our y to be equal to what? U exponent 4, because we are saying that u is equal to the function inside. So we are going to get our y, which is the function, to be in this form, u exponent what? 4. Now what we are going to do here is we are going to differentiate the function u with respect to x. So we are going to get du dx. So when we differentiate 3x, we are going to get what? 3. And then what we are going to do here is we are going to differentiate the function y with respect to u. So it's going to be dy du. So when we differentiate u exponent, you subtract 1 from the exponent, we are going to get 3. So after that, we just write the formula down and then we do our substitution. So we know that our dy dx is giving us dy du times du dx. So our dy du, we had 4 u exponent 3, and then our du dx, we had what? 3. Now 3 times 4 will give us what? 12. But remember, u was defined as what? So we are going to get 3x plus 1 all exponent 3, and that is that. So you can see that the two methods are yielding the same solution. So whichever way method you are going to use, you are going to get the same answer. Let's try the next example. So we have the second example. We have to find the derivative of h prime at s of this very function. So the first thing we are going to do is identify our inside function and then our outside function. So our inside function, which is g at x, is going to be what? S squared minus 4. So we have s squared minus 4. And then we identify our outside function, which is f at, okay, let's make it f at g at x so that you see it well. And this is going to give us what? S squared minus 4 all power 3. Now what we are going to do next is we find the derivative of g at x, which is going to give us g prime at x. When we differentiate s squared, we are going to get what? 2x. We differentiate a constant, we get 0. And then f prime at g at x, when we differentiate this using the product, we are going to get 3 out, s squared minus 4, and then you subtract 1 from the exponent, we are getting 2. So after that, we just substitute this into the formula, which says that our h prime at x is f prime at g at x times g prime at x. So when we do the substitution, our f prime at g at x is giving us this very part. So we have 3 s squared minus 4 raised to the power 2 multiplying g prime at x, and g prime at x is what? 2x. So let's see if you can expand. So 2x times 3 will give us what? 6x. And then we have x squared minus 4 raised to the power 2. We can leave our answer in this very form. So this is the derivative of this function. And we are also going to use the Leibniz approach to see if we are going to get the same answer. So we know that our function y is given as what? X squared minus 4 raised to the power 3. So we are just going to let our u be equal to the function inside. So we have x squared minus 4. Therefore, our y, the function y, will be equal to what? U exponent 3. So the next thing we are going to do here is to find our du dx. So we are going to differentiate u with respect to x, and that is going to give us du dx. So when we differentiate x squared, we are going to get 2x. We differentiate a constant, we are getting 0. Then we are going to find the y du. We are going to differentiate the function y with respect to u. So we are going to get the dy du u exponent 2. So all what we are going to do here is just substitute these functions and their derivative into the formula. So we are going to get our dy dx is given as what? Dy du times what? Du dx. And this implies that we are going to get our dy du is given as dy, where is it? Dy du. Okay, so this is dy du. We are getting 3u squared multiplying du dx. Where is it? So we have 2x. So you know that 2x times 3 will give us what? 6x. And then we have u squared. But we have already defined u to be what? X squared minus 4. So we just come and substitute that one here. So at the end, we are going to get our dy dx being equal to 6x bracket x squared minus 4 all squared. So you can see that the answer that we are getting here is the same answer that we had here. So no matter the method that you are going to use, you are going to get the same answer. We try the next example. So we have the function h at x, and then we have to find the derivative of this very function. So we know that this function here can be written in an index form. So we can rewrite h at x in the form of 2x squared plus 1 all raised to the power half. You know that the root sign is the same as what? Half. Now that we have written in this very form, let's identify our inside function and then our outside function. So we call our inside function g at x, and that is what? 2x squared plus 1. And then we find our outside function, which is f at g at x, and that is going to be 2x squared plus 1 all raised to the power half. Then after that, we find the derivative of each of them. So we know that the derivative of g at x is given as what? G prime at x. So when we differentiate 2x squared, we are going to get 4x applying the power rule, and the derivative of a constant is 0. Now we find the derivative of f prime at g at x. Now when we differentiate using the power rule, this half will come in front. So we write what is inside plus 1, and then we subtract 1 from the exponent. So we are going to get half minus 1, we are going to get what? Minus half. I believe you can see it. So minus half. Then after that, we just substitute these functions and their derivative into the formula. So we know that h prime at x is giving us this. So we just have to do our normal substitution. So we know that our f prime at x is equal to this very part, and then our g prime at x is giving us 4x. So all we are going to do here is to just simplify them. Okay, we know that this raised to the power negative half can be written as 1 all over 2 bracket 2x squared plus 1 exponent half. So we have r times 4x. Okay, now we can also rewrite this in this very form. We know that any variable raised to the power half is what? The root, or half is also known as what? The radical sign. So we can write this in the form of 1 over 2 root of 2x squared plus 1, and then we have 4x times 1 will give us what? 4x. And we know that 2 can cancel the 4, so we are going to get here to be 2 will go, and then we are left with 2 here. So finally our answer is going to be 2x all over root of 2x squared plus 1. Now you can use the Leibniz approach to find this derivative also, so I'm not going to do it. We are just going to look at the next example. So we have y equals to 3 over 2x plus 5. We have to find the derivative of this very function y. So we know that this 3 over 2x plus 5 can be written in an index form. Okay, so we can write this, our function y, in the form of 3. We have our 2x plus 5 raised to the power negative 1. I believe you remember, when you have 1 over x, we can write it as x exponent negative 1. So that is what we have applied here. Now the next thing that we are going to do here, this one I'm going to use the Leibniz method. So we are going to identify our u. Okay, so from here our u is going to be what? 2x plus 5. Therefore our y, the function y, is going to be what? Yeah, it's going to be what? 3u. This is the 3, this u, and then exponent negative 1. Now what we are going to do here is to find our du dx and then the y du. So we are just going to differentiate the function u with respect to s, and this and that is going to give us du dx is going to give us, when we differentiate 2x, we are getting what? 2. Very good. Then we come to this very part. We are going to differentiate this function y with respect to u. So we are going to get dy du. Now applying the power rule, the negative will come and multiply the 3. We are going to get negative 3 u. Then we subtract 1 from the exponent. So when we subtract 1, let me indicate it so that you see it well. Now when we subtract 1, we are going to get what? Minus 2. And then we just substitute these functions and their derivative into the formula. So you know that our dy dx is giving us dy du times what? Du dx. Now our dy du is giving us what? Dy du is giving us minus 3 u exponent negative 2 multiplying du dx. We had what? 2. Good. Let me continue from here. So let's multiply 3 times negative 3. 2 times negative 3 will give us negative 6 u exponent negative 2. Now we know that u has been defined to be what? 2x plus 5. So we just come and substitute this in place of u. So we are going to get negative 6 bracket, we have 2x plus 5 raised to the power negative 2. Now the last step we are going to do, we can leave it here, but the last step we are going to do is to write it in a very nice form. So we can get or write it in the form of minus 6 all over 2x plus 5 raised to the power 2. And this is the derivative of the function y. Now remember, we can also use the quotient rule to solve this very question as we did in our previous lesson. So we have our y is equal to 3 all over 2x plus 5. So the quotient rule says that, so you can say our dy dx is equal to, now we keep down, when we keep the down is 2x plus 5. We keep down, we differentiate top. Now when we differentiate the top, which is 3, a constant, we are getting 0, minus, we keep top, which is 3, and then we differentiate down. The down is 2x plus 5. When we differentiate it, we are getting what? 2 all over what? The down squared. The down squared is 2x plus 5, and then we square it. So at the end, we are going to get 0 times the whole of this, we are going to get 0, and then we are going to get minus 6 all over 2x plus 5 all squared. So we can use the quotient rule. If you have forgotten, you can go back and watch the video. So we have this example. We have to find the y dx, which is known as what? The derivative of the function. So we know that this function y can be written as 1 out of 2 plus x squared all raised to the power of half, because the radical sign, which is the square root, is the same as what? Half. And this can also be written as what? 1 out in an index form. So we have 2 plus x squared raised to the power negative half. Good. So now our function is 2 plus x squared raised to the power negative half. Very simple. So we are just going to apply any of the two methods, whether the Leibniz method or the other one. So let's use the Leibniz method. So we are going to let our u, equal to 2 plus x squared. So our function y will become what? It will become u exponent negative 1 over 2. So we are going to differentiate this function du with respect to x. That is going to give us du dx. And we are going to get, when we differentiate a constant, we are getting 0. When we differentiate x squared, we are getting what? 2x. Now we are also going to differentiate the function y with respect to u. So we are going to get dy du. And using the power rule, we are going to get minus 1 over 2 u raised to the power positive half. So the next step is to just substitute these functions and their derivative into the formula. So we know that dy dx is given as dy du times what? Du dx. And we know that dy du, we had minus 1 over 2 u exponent 1 over 2 times du dx, we are getting 2x. Now 2x times half, we are going to get minus 2x all over 2 u raised to the power half. We know that this and that will go, we'll be left with x u exponent u raised to the power half. Now we have already defined u in terms of x, so we know that u is equal to this. So we are going to get x bracket 2 plus x squared all raised to the power half. And we can rewrite this in terms of x bracket square root of 2 plus x squared. And that is that. You can also use the quotient rule to solve this very question. Thanks for watching.